Yeah, that was pretty sweet. Didn't want it. He didn't look like he knew how to shoot basketball either. Don't want like.
Let's consider modeling with higher order equations. So here is a second order initial value problem. AY double prime plus BY prime plus CY equals some G of T. Now, A, B, and C are constants in this scenario. They're just numbers. And this G of T in this particular format is either called the input function, the driving function, or the forcing function. When I deal with mechanical systems, we often call it the forcing function. When I deal with electrical systems, we often call it the driving. No, forcing for mechanical, driving for electrical. I think that's right. And Y is called the response function. The output function. My favorite example of this is this flashback to the physics class here. This is one of these. All right, wait a minute. A hanging spring. In this case, that mass is, I believe, 550 grams. But it's pulling down a spring here. And I know that there's a force acting on this. What is the force's relationship to the position of that hanging mass? Oh, wait a second. Newton's second law. What's Newton's second law tells me? Tell me. Technically, no, that's the third one. That's the first one. F equals ma. We went through all three of them. We got there eventually. But acceleration is the second derivative of position. So if I think of a position function, then I can think of this as a second derivative. Now, I've let that spring hang there for a while so that this would slow down and stop bouncing. Let's assume for the moment that this mass is in equilibrium. It's not moving. We're assuming. If it's not moving, then there's something countering gravity. There's another force. And what force is that? What force is acting opposite to the force of gravity, Fg, here? The spring itself. And there's a guy in the physics class we talked about named Hooke. Hooke's law tells me that the force exerted by the spring is negative some constant times x, where x, in this case, is the displacement from rest. Well, if that spring is in equilibrium and it's not moving up and down, then these two forces are equal. And I would have mass times gravity equal to negative K times the stretch. Now, when I talk about the stretch here, if I take the displacement, if I take the weight off the spring, that's its unstretched length, put the weight on the spring, that's the displacement. Oh, wait a second. So I use this to find the value of K. So I can take any spring, this spring, for example. I could take the weight off. Got a meter stick here. I can tell you how long this is. Turn it so it's actually facing the right direction. See centimeter. I say, oh, without the weight on it, here's the length of the spring. Somebody tell me where my finger's at on the meter stick. 45. 45? So it's a 15 centimeter stretch. 0.15 meters. Gravity's in meters. The weight's 550.55 kilograms. I can figure out X. Figure out K. So now, by the way, I've oriented this in a particular direction. Notice that mass times gravity is a positive number there. Down is the positive direction. I said there was a 15 centimeter stretch. It's going down. So that's a positive 15. So I'm considering down to be the positive direction. And let it go. What's going to happen? I let go. Wait a second. Bouncing. That's a trig function. My acceleration has now been changed because that's in motion. It's accelerating. So I actually have a second order differential equation. And it's homogeneous. Which means I can solve it. In order to solve this, I need to get the corresponding auxiliary equation and all that fun stuff, right? It's easier probably if I divide by m first. Let's call this number W. K over X. Actually, you know what? I think we call that the W squared. I promise there's a reason for using a square here. What's the corresponding auxiliary equation to that setup? This isn't a Cauchy-Euler equation because the coefficients are constants. A solution to that. What are the roots? Find me YC. the corresponding homogeneous solution. Which means this should be going on your formula sheet. I have complex numbers. The W would be
like plus.
the W goes in with the cosine, inside the cosine. If my original stretch was some known number, right? We were at 15 centimeters here. I stretch it down, say 5 centimeters, and I let it go. But I'm holding it at rest. What's the initial velocity? 0. And the initial position is however far I stretch down. I said 5, right? We have an initial value problem. We can solve for C1 and C2, right? At time 0, we know, sorry, technically, I just realized I've written Y. That's not the right letter. What's the name of the function I'm dealing with here? It's x of t, position. So this shouldn't be yc, this should be xc. And then I know x of 0 is my starting position, and x prime of 0 is my starting speed. And I can solve for C1 and C2, provided I know K. But this is a trig function. It's just bouncing up and down. As a matter of fact, what happens when you plug in 0 here? I just get C1, right? Well, C1 cosine of 0, that's C1 of 0, that's times 1. Yeah, so I get C1. So if that C1 is 5. That made my life easy. 0.05, I should be in meters per second. And then the same thing I can do C2 when I take the first derivative. Because the sign will be on C1 and sine of 0 is 0. I'll get C2. If I'm at rest, what's the value of C2? It's 0. Which means this is just a cosine equation, isn't it? Simple harmonic motion. I get a trig function. By the way, the W here, technically, it's the Greek letter omega, is our angular velocity idea. We have a period here. The period of this trig function is 2 pi divided by omega. It's t. That's time. The frequency here is 1 over t, number of vibrations per second. The unit for that is hertz, usually abbreviated Hz, but that's vibrations per second. And omega, this W we were looking at, that's the square root of k over m. That's where we got it from. That's our angular frequency. Now, depending on which book you read, that's also referred to as the natural frequency. Sometimes they use the 2 pi over omega, the natural period instead. When I set this up, I started with mass times gravity to get weight. When I'm in metric, I have to use gravity as 9.8. When I'm in imperial units, when we use pounds, pounds is already force. If I say the weight is 2 pounds, that includes mass and gravity already. I don't have to worry about that. We did this with the skydiver. We needed the gravity was 32 feet per second squared. If I'm talking about pounds, gravity is already incorporated into that. I don't need to worry about it. So let's suppose that I have a weight of 24 pounds. Oh, I probably mentioned this at least in one class before. Does anybody know why the abbreviation for pounds is LBS? Ah. How do you weigh something back in the oldie days? Oh, yeah, but if I want to make it a precise weight, a scale. What's Greek for scale?
LPS.
Almost.
LP.
Libra, your sign, right? The sign Libra is the scales. Librum. Librum poundum, the weight on the scale. LBS.
So a Libra is a scale.
A Libra is a scale. Like a Pisces is a fish. A Libra is a scale.
You know?
All I remember is that was a long time ago, and the 70s were weird. But if I have this particular weight and it's on a starting position, y0, x0, sorry, x0 is minus 1/4 of a foot. Why am I in feet? Oh, right, because pounds. Pounds is using feet, imperial system. We'll go with the starting velocity is 0 feet per second. And when I put the weight on, where did I pull this number out of my ass? Where's that? Yes. When I put the weight on the string, the stretch from unweighted is S equals 4 inches. I just want to set this thing up. Let me see if I can set this thing up. I need the spring constant. I need to know what the K is for the spring in this problem with this 24-pound load on the end of it. How do I figure that out? If you took physics already, you did this lab experiment. If you're taking physics, you're doing it next week. How do I find the spring constant? What length? Because there are a couple lengths up there right now. We wrote the equation down to help us figure out the constant. I watched y'all write it down. I wrote it down.
Force equals negative.
Aha. And the force in this case is the force of the weight pulling down. And the stretch, our x is the displacement there, right? What's our displacement? Oh, that's our starting position.
Oh,
Aha. Wait a minute. I should be in feet. 4 inches is how many inches in a foot?
well, well,
So it should be 4/12 of a foot. Okay. So if I want the K, the force of gravity, that's the weight, should be equal to K times the stretch. What's the value of K? Now, here's the weird part about that number. What again? Well, I'm dividing by that, right? So that's pounds per foot. That's a measure of force, right? As I stretch more, it pulls the other way with a force in pounds for every foot I stretch it. So the units on that are really weird. They're pounds per foot. Now, for every spring, that constant is different. It depends on the material the spring is made from, the size of the wire, the tightness of the coil, the rigidity of the material. There's all sorts of stuff that goes into calculating this beforehand. I'm not going to do any of that shit. I'm just going to measure it by putting weight on it.
shouldn't there be a negative? Okay. Or
Um,
are we using down?
I'm doing down as positive, yeah. So if I go back to my setup needed that W, right? How do I get W? Which means I need M. Do I have M? I have weight. How do I get mass? But negative with kx is 24, right? Because that's what this is right here, k times x. So that's 20. So it's just the mass. Because remember, mass times gravity is equal to force. So our weight here is 24 pounds. That's mass. And now I need the 32 for the gravity. That's positive. So I get mass is 24 over 32. Six over 8, 3 over 4. Now here's the again, weirdness of units. That's pounds divided by feet per second squared. So that's pounds second squared over feet. What the? Nobody uses this unit. This is called a slug, and that's the only time you'll ever hear me say that. But now I have our M, I have K, so I can get my frequency. My circular frequency is the square root of K over M. Simplify that. 72 divided by 3/4. Beg your pardon? 96. 72 divided by 3/4 has got to be an even. Yes, that's square root of 96. All right, wait a minute. 96 is divisible by 4. So it'll be 4 times 24. 24 is also divisible by 4, right? So that's divisible by 16, which makes it 4 square root 6. If you want to simplify, you don't have to. But now I know omega, which means I know that x of t is C1 cosine square root 96t plus C2 sine square root 96t. And way back up here, the top, just off the top of the screen, we wrote down an initial position and an initial velocity, which means I can solve for C1 and C2. Please do so. I know it's a ballpoint with a click button. It should have another spring. But I don't have another spring. I'll let it lie. I was hoping I don't have a ballpoint that clicks in my bag either. I'm like, damn it, I don't have any of these. Teach me to raid the physics lab and only get half the stuff. It's not important. Thank you. If I plug in t equals 0 and I just put the position in, I get negative 1/4 equals C1 cosine of 0 plus C2 sine of 0, but sine of 0 is 0. So I get C1, and that means that C1 is negative 1/4. That was nice and easy. Take the derivative. The derivative of cosine, this is not supposed to stump the room. So I get negative C1 sine square root 96t with another square root of 96. Oh, wait, I got to put in 0 there. Let me write this as just x prime. Plus derivative of sine is square root 96t square root 96. So x prime at 0 is 0. Put in 0, I get negative C1 times sine of 0 times square root of 96 plus C2 times the cosine of 0 times the square root of 96. So what's C2? Because that goes away. What's C2? Yay. So x of t is negative 1/4 cosine square root 96t. Now, my first question to you, if this cosine is negative, does that make sense? Well, our x0 was negative 1/4, right? Means I start, my weight held up a bit, and then I let it go. So it starts in its motion from the negative side, because we said down was positive. Starts up here, which is negative, and becomes positive. So that does make sense for a cosine to go this way.
We have the x of c is c1 cosine plus c2 sine because of the I, right?
Yeah. Now, I also will say we just got a very rigged problem because we started with our weight held up at rest. So we got C2 equals 0. But if my object is not started at rest, if it's started at motion, if I give it a push to start it, then I will get two different C1s. If both C1 and C2 are not 0, this is a little messier. So if you take a look in the textbook at problem number 9 in this section, it goes through a very similar problem. Ready? A mass weighing 8 pounds. Determine the equation of motion if the spring constant is 1 pound per foot. Initially released from a point 6 inches below equilibrium with a downward velocity of 3/2 feet per second. Well, that means that I'm going to get x of 0 is 1/2 because we're a foot down. And x prime of 0 is 3/2 because we start by pushing downward. When I work through this, I will get y equals 1/2 cosine 2t plus 3/4 sine 2t. Do me a favor, grab your graphing calculator. Graph that. Of course you can guess. Say again? Unfortunately, no. I just said this was going to get more complicated, didn't I? It doesn't look any more complicated. It just looks like a trig function, right? But it's 2. It's a sine of 2t and a cosine of 2t. That's what I graphed. 1/2 cosine 2x plus 3/4 sine 2x. That's this expression right here. Why do I only have one trig function? Long ago in a classroom far, far away, you actually did learn this. When you add two trig functions, cosine and sine, and they have the same period, they reinforce one another. we have constructive interference. And we end up with a single trig function. But it's not starting at 0. It's not starting at 1. Remember, cosine starts up here at the top and goes down. Sine starts at 0 and goes up. This is shifted. Trig class, we talked about amplitude and period and phase shift. That's a phase shift. It turns out C1 cosine omega t plus C2 sine omega t can be written two different ways. It can be written as A sine omega t plus phi, where A is the square root of C1 squared plus C2 squared. Our amplitude grows, and phi is our phase shift. Tangent of phi is, wait a minute, tangent, C1 over C2. Or I can write it as A cosine omega t plus, I need a different letter, theta. A is the same thing. And tangent of theta is C2 over C1. Or you could remember it by saying, oh, I'm doing cosine. Let's do a cotangent, and then the fraction stays the same. C1 over C2. Which means I can turn this trig function into one trig function. And whether you want to write it as a sine or a cosine, I don't care. You can write it either way. I just have to find the amplitude and the phase shift for whichever version I want. For our particular example, what's the new amplitude? What's the height of that trig function? Well, if I go back and I look, this window is only 2 units tall. So it's actually really close to 1, I think. But the first one is the height of 1/2, and the second one's the height of 3/4. So they're adding to each other, but it's not going bigger than 1 because it's going according to this. So in our example, the amplitude, 1/2 squared plus 3/4 squared is all right. If I'm over 16, then 1/4 has to become 4/16. And I'm going to get 9 and 4 is 13 over 16. Or square root of 13 divided by 4. What is that number? Really damn close to 1, right? 0.9. Well, that makes sense. Looks right. Compare the height here with that mark at 1. I'll buy that. It's shifted. If we think of it as a sine curve, then it is shifted a little bit to the left. Because if it was a sine curve, this point where we cross the x-axis should go through 0. If it's a cosine curve, then it's shifted to the right because this part should be the y-intercept. And that's why there are two different versions of the angle, depending on whether you want to think of this as shifted to the left or shifted to the right. So C1 over C2. Is 1/2 over 3/4, which is 2/3. So what you need is an angle, either whose tangent is 2/3 or whose tangent is 3/2. And then I can get with my inverse tangent button. Tangent inverse of 2/3 is a disgusting angle. Call it 0.588. If I'm using the tangent, I'm using sine. So square root of 13 over 4 sine 2t plus 0.588. I claim if you graph that, you should get the same picture. You could also do the cosine. Square root 13 over 4 cosine 2t what? Well, now I need an angle whose tangent inverse is 3 over 2 instead of 2 over 3, 0.973, 983. Graph both of these. If we don't have one picture, we done put some up. Every free vibration is a single trig function. Questions? I see more things for your formula sheet. I forgot to bring them. What if you have two springs instead of just one? You could have got it in a couple of different ways, right? You could put one spring attached to the other. Or you could put both springs attached to the bar and to the weight. That would change how stretchy they were, wouldn't it? All right. If the two springs are attached to each other, we say that they are in series. If the two are both attached to the bar and the weight, we say they are in parallel. Gee, I hope it's clear why we call them parallel. It looks like parallel lines. There we go. Notice these two springs are slightly different colors. That's to represent the fact they have different constants. They don't have to be the same spring. Here, they have different constants. They're different springs. So what I get is I get a new thing. Instead of just having one spring, I have to combine these somehow. I get what's called an effective spring constant. Which we'll call K effective, K-E-F-F, subscript. And depending on our setup, we compute these in two different ways. For a parallel, the two springs are side by side, the effective spring constant is just the sum of the two. They're both pulling, you count them both. But when they're in series, they behave reciprocally. 1 over the effective is 1 over the first one plus 1 over the second one. If you want to solve this for K effective, you could write that K effective is K1 times K2 over K1 plus K2. But I can never remember that formula. I always just remember flip them over. No matter how many springs I've got, I can take all the different parallel and series and add and reciprocal until I get one effective spring. I just have a new constant for that based on the pieces it's made up from. This is why you don't do part coil replacements on a car. You either replace the whole coil or you leave the damn thing. Because if you mix coils, you'll change the spring constant. One will have been worn and will be a weaker spring than the other. You get different constants, you get different bounce on the side of your car. It's not a good thing. But springs age. I just said that. My shock absorbers in my car are, I don't know, 10 years old, 8 years old. I don't remember the last time I got the struts and stocks changed. Shocks changed. But what happens over time is the spring wears, which means this K can change over time. And if K changes over time, I might want to use a function instead of a number. Usually, we model the aging of a spring by saying that the constant gets more and more close to 0 over time. As the spring ages, it becomes less resilient. And if it's less resilient, then, oh, crud, my spring constant is not, it's not resisting anymore, right? The resistance of my spring became 0. What happens if the resistance of my spring becomes 0? It basically snaps. So I get much bouncier as my spring gets weaker. Alternately, what happens in the winter? What happens to metal in the winter? Well, not necessarily, because metal is really hard. It becomes stiffer and breaks easier. If it becomes stiffer, then my constant should get bigger over time, not smaller. And when we do such a thing, we get a system where it's stiffer when it's cooler. Well, I can talk about K getting replaced by, I don't know, just a linear function, for example. Well, then I would have mass times acceleration plus kt x equals 0. That's not quite a Cauchy-Euler equation. But these equations were studied rather thoroughly, and they're called Airy equations, A-I-R-Y. These are harder to solve because they're not constant coefficients. The constant coefficients ones are easy. I have a question for you, though. If my spring is supposed to behave like that, why didn't it? Resistance to what? There's a damping factor going on here. There's stuff pushing against this weight as it moves through the air. So I want to figure out how to take that into account. because my spring came to a stop. And this equation didn't. So what's different in my model if I need to take into account air resistance? Or, like with a shock absorber, there's a hydraulic fluid around the spring that does the same thing. It absorbs energy as the spring vibrates. If you have a door closer, this door doesn't have one, I pointed this door, like across the hall in 358. You open that door, there's a mechanical arm that will close the door. It's a spring pulling, but the door doesn't slam shut. You got a screen door at home, slams all the time because the spring is overdamped. We'll talk about the damping on Monday. I will see you all then. Have a lovely weekend. I hope so.